which of these two functions grows faster, e to the x or x cubed? We're going to use that idea of the limit of the ratio of these two functions to come up with our answer here, right? Because if we think about it initially, okay, well, if x is 1, well, this e is, approximately 2.7. 1 cubed is 1. If x is 2, well, now we have 2.7 squared versus 2 cubed. And then if x is 3, then we have 2.7-ish to the third power, whereas this is 3 to the third power. And then what if x is 4, or 5, or 6? But more importantly, what if x is 100? All right, e to the 100th power versus 100 cubed. All right, now the numbers start getting a little bit, too much perhaps for our brains to kind of comprehend. So let's use the limit to help us decide what's going on here, right? So if we take the limit as x approaches infinity, because ultimately that's what we're interested in, extremely large values of x. And we've got e to the x in the numerator, and we've got x cubed in the denominator. Now, if we want to try and find this, well, if we plug in a very large number, we know the numerator is heading towards infinity, the denominator is heading towards infinity, so that gives us a limit which does not exist. So let's use L'Hopital's rule. Right? And when we do so, we still have the limit as x approaches infinity. Our numerator is the derivative of e to the x, which, yes, is e to the x. And our derivative of the denominator would be, good, 3x squared. All right, so we have that situation right there. We're taking the limit as x approaches infinity. I think we can all see here that the numerator is still heading towards infinity. The denominator is still heading towards infinity. So we know from L'Hopital's rule, that's okay, we can just derive again. And we can continue to do that as long as we have an indeterminate form. So this becomes the limit as x approaches infinity of derivative of e to the x, which once again is e to the x, over the derivative of 3x squared, which is 6x. And once again, this gives us an infinity in the numerator, infinity in the denominator. So let's do it one more time. And when we do so, we now have the limit as x approaches infinity. And our numerator is the derivative of e to the x, which is e to the x. Our denominator is just 6. And when we plug in a very large number for x, we see that we have e to a very large number in the numerator, but we're only dividing it by 6. All right, so this is going to be unbounded. So this limit does not exist. All right, or if it goes to infinity, if we can go that way. And therefore, we can now verify that e to the x is our function which grows faster among the two. Okay. Even when we're comparing e to the millionth power over a million cubed, well, we can see here what's going to happen. We can see that the e to the millionth power is going to be much larger. All right, exponential functions in general, well, it doesn't matter if e to the x, 2 to the x, 3 to the x, whatever, they will grow faster than polynomials. Right? And this verifies this. And it doesn't really matter what the polynomial is. Think about this. What if this was, instead of x cubed, what if it was x to the 100th? All right, well, if we derive that, we then have 100x to the 99th. All right, and so on later. Eventually, what we're going to get down to is 100 times 99 times 98 times 97, which we mentioned in a previous video. That's the factorial. This would ultimately end up being e to the x in the numerator and 100 factorial in the denominator. 100 factorial is still just a number, and e divided by, again, the limit as x approaches infinity, all right, then we can still see that that's divergent there. So e to the x is still larger than x to the 100th power. All right, and in general, exponential functions are going to grow faster than polynomial functions. And that's the idea behind this, this growth comparison. It's going to allow us to have a better idea when we're talking about functions that are a bit more complicated than just e to the x or just a polynomial. What if we had a combination of them?